Welcome everyone to this lecture on a TensorFlow regression example. We're going to code along for a more realistic regression example, and we'll also introduce TensorFlow's tf.estimator API, which is a much simpler API for basic tasks like regression and classification. There are already lots of machine learning algorithms that can perform regression tasks and classification tasks very well, and the purpose of TensorFlow really is to try to solve problems that typical machine learning algorithms can't solve. Things like image classification, or later on we'll see how we can use TensorFlow for things like word embeddings, or even using recurrent neural networks for time series analysis. Those are problems that are really hard to solve without the use of a deep neural network or specialized neural networks using TensorFlow. Simpler examples like typical regression tasks and classification tasks are pretty easy to solve, well, depending on your data set, with other machine learning algorithms. And because of that, TensorFlow has a nice estimator API that's going to make your life a lot easier if you decide to use TensorFlow for some of these more basic supervised learning problems. So let's go ahead, hop over to a Jupyter Notebook, and show you how to perform a regression task on a more realistic data set. Alright, I'm going to start off with a couple of imports. I'll do NumPy as NP. I'm also going to be using pandas, and I will import matplotlib.pyplot as plt and then set matplotlib inline. And then later on we're also going to need to use TensorFlow, of course, so let's do that as well. Import TensorFlow as tf. Okay, what we're going to do for this regression task is do a huge data set. So we're going to actually create a very large data set. And in the next lectures, when we actually cover classification, we'll use a real data set for that. But right now, I still want to do a gradual progression from the last lecture, so we'll create our own data set. So I'm going to say linearly spaced from, we'll say 0.0 to 10. And instead of just 10 points, we're now going to do 1,000,000 points. So this is a huge data set, so we're not going to be able to do exactly what we did before. And then I'm also going to add some noise to it, just like we did last time. So I'm going to say noise is random.randn. And we need to pass in length of data so we know how many noise points to have. So if I take a look at my x data, it's essentially just these evenly spaced values. You can see there's 1,000,000 of them, so the step size is really small. It's like 0.000001 step size. And then if I take a look at my noise, at least the shape of it, I can see I essentially have 1,000,000 random points from this normal distribution. So just a bunch of random points that I'm going to add on to that. Let's go ahead and create those. So I will have the following function. My line is going to be modeled by y is equal to mx plus b. And I'm going to set b equal to 5 for this model. And then I'm also going to add in some noise. So I'm going to add in the noise levels. So let's actually do this. We'll say that y true is equal to, let's choose a slope of 0.5, and then I'm going to multiply that by my x data, and then I'm going to do plus 5 here. So I have m equal to 0.5, and that's something that we're going to try to figure out using our model, and then I'm also going to have b equal to plus 5. And to make it a little harder for our model, I'm going to put in some noise here. So now we have our y true values, again just following y equals mx plus b, where our slope is 0.5, our intercept value is 5, and I've added some noise to it so it's not just a perfect fitted line. Now let's actually create this data, and I'm going to use pandas to kind of concatenate some stuff together and also make plotting a little easier. So I will say my data is equal to, and I'm going to say pd.concat, which is short for concatenate, and we'll see how we use that in a second, but before we do that, over here, I'm going to create a data frame. So let's first make our x data frame. So we'll say xdf is equal to pd.dataframe, and the data is going to be equal to my x data, and the columns are just going to be equal to x data. So there's my x data frame, and then I'm going to also create my y data frame. So we'll say ydf is equal to pd data frame. Data, as you might have guessed, is equal to y true, and the columns are going to be equal to, let's just say y. Alright, so I have my two data frames, and if I check them out right now, I can say xdf, let's just check the head of that data frame, the first 5 rows. So there's my X data. I can see it's going along very slowly, step size. And then if I take a look at YDF, there are my Y values, and you can see here the noise has definitely been added in there. Let's go ahead and concatenate these two so that I have these two columns together. So the way you concatenate two data frames is quite simple. You just say pd.concat, and then I'm going to pass in a list of the data frames I want to concatenate together. So we have YDF, and then I also want to do X data. So let's actually do XDF first. So XDF, YDF, and I want to concatenate them along axis is equal to 1 because I want to do it along the columns. So as a second parameter here, I will say axis is equal to 1. If I didn't have that axis argument, it would kind of stack them like pancakes, if that makes sense. And now if I take a look at my data, there it is. I have X data and Y. So a lot of that there. Let's just get the head of it. So the reason I did that is because it's going to make it a lot easier to actually plot this out. If I were to try to say my data dot plot, that's going to take a really long time, and it may actually cause the kernel to crash because it's going to try to plot 1,000,000 points. Instead, let's just plot a small sample of that. And the way we can do that is really easy with a pandas data frame, which is kind of the whole point we did that. All I need to say is my data dot sample n equals, let's say 250, and then that's going to return back 250 random samples. You can see here by the index that these are just random samples of the data frame. So here I have 250 random samples. This is a small enough thing that I can plot out. So now I'm going to call plot off of this, and I'm going to say that the kind of plot I want is a scatter plot, and let's say x is equal to x data and y is equal to y. So now let's run that, and here's my plot. So I can see here my data is going from 0 to 10 on the x-axis, also from 0 to around 11-ish on the y true label, and that's because we added in some noise on some of these points. So you can see here definitely a linear trend, and you can see that we've added some points off of that line. So the true line right here, remember y true is defined as a slope of 0.5 multiplied by the x data. The intercept is at 5, so if we scroll down here we can see that it would intercept around 5 if there's kind of a linear fit here, and then there's some noise up and down off of that. So we want TensorFlow to try to fit a line here, and we should see it kind of go very close to 5 as the intercept and have a slope of 0.5. Let's go ahead and see how TensorFlow can make this happen. The first thing we have to realize is that 1,000,000 points is a huge amount of points to pass in at once. And a lot of times when you're dealing with deep learning and just neural networks in general, you're going to have humongous data sets because the more data, the better, usually, for training a lot of these complex models. But the problem is you can't just feed in 1,000,000 points into your neural network at once. So what you do instead is you create batches of data. You feed in batches of the data for training batch by batch. Let's go ahead and show you how to do that. So I'm going to say my batch size, create a variable, is equal to 8. So I'm going to grab 8 points at a time. And you can also change this around, so maybe 10 points at a time, 12 points at a time. There's no true right or wrong answer for batch sizes. Certain batch sizes really depend on your data. Obviously, if I only had 8 data points, then batches wouldn't really make sense. If I have, 1 trillion data points, maybe do larger batches. Otherwise, you'll be waiting all day and you won't use all your data. So right now, batch size 8, that's fine. And we're going to create our m variable just like we did last time. So that's the slope, remember. And let's go ahead and just start it off as 0.5. And we'll say b is equal to tf variable. And that's going to be 1.0. And let's actually make these random numbers again, just so we show that the network's actually working. So we'll say np random rand in, let's rand and n. And let's give me 2 of these guys. Okay, so there are my 2 random numbers. We're going to grab these and insert them. There we go. And we'll grab this one as well and insert that. Okay, so now I have my 2 random numbers. We could have also initiated that as negative, not a big deal. But you can see here, I'm choosing just 2 random numbers to initiate my slope and my intercept, just like I did in the last lecture. So I have my variables here. Now let's create our placeholders. And now we're going to have 2 placeholders, one for the x and one for the y. So I have my x placeholder, tf placeholder, and it should be a 32-bit float. And the size, we're just going to say batch size. So we're going to feed it in batches. So we'll feed in 8 points at a time, and it's going to be the exact same thing for the YPH. So I can actually just copy and paste this here. Okay, so I want you to kind of get used to this workflow of first creating the variables, then creating the placeholders. Then the next thing we need to do is actually define our graph. In other words, the actual operations that are taking place. So what are we trying to do here? Remember, we're trying to build a y model that models out at y equals mx plus b. So I have m as my placeholder. I'm going to multiply it by, or excuse me, I have m as my variable that I'm trying to adjust. Remember, that's kind of a weight slope that I'm trying to adjust. And I have x as my placeholder. That's going to be fed in data through a feed dictionary. And then I'm going to say plus b, another variable. So right now my model is right here, y model, and this is essentially my graph that I'm trying to compute. Then we need a loss function, and we're going to use some TF tools to kind of make this into one nice one-liner. So we have tf.reduce sum, and I'm going to say tf square of y placeholder. Remember, that is the true y value. Subtract our actual prediction. Whoops, y model, y underscore model. Okay, there we go. So this is our loss function. Again, essentially the same thing we did last time, except now I'm using tf square for these kind of convenience functions here. Now I could also, instead of saying tf square, do something like asterisk asterisk 2, but to kind of match up with the documentation, it's nice to use these TensorFlow optimized function calls. Up next, once we have our loss function, it's time for the optimizer. So let's put it in. We're going to say optimizer is equal to tf train, and we're going to use the same thing we did last time, which is call a gradient descent optimizer. Later on we'll discover other optimizers, but we're going to set a learning rate, and let's go ahead and just set it to 0.001. And then we actually want to tell the optimizer what to minimize. Let me make sure I put this with an E in there so I don't get any spelling errors. And then we'll say optimizer minimize the error we just made. Okay, so I have done the key steps here, created my variables, created my placeholders, defined my graph, essentially defining the operations. I've defined my loss function here, and then I have my optimizer, which is trained to use gradient descent to minimize that loss function or that error. Now let's go ahead and create our init variable for initializing the variable. So we'll say init is equal to tf global variables initializer. And let's run this session. So we're going to do the following. We'll say with tf session as sess. First thing I need to do is run that init so it actually initializes those variables. And then now I have to decide how many batches I'm actually going to run through this. So let's do 1,000 batches. We'll kind of play around with this. So you can play around with this number right here, batches, and this number right here, batch size. So I'm going to run this through 8,000 samples and see if that's enough for it to fit a nice linear fit here. And it really should be enough because we're not adding that much noise. And even with kind of our eyeballs, we can see here that there's clearly a linear trend. So the model should be able to pick it up quite clearly. Even with 8,000 samples, it should be enough. We don't need to feed it in 1,000,000 samples, although we could and get, maybe overfit to our training data. But we'll discuss that later. We'll say for I in range batches. So we're going to send 1,000 batches in. Then we'll do the following. We'll say some random index is equal to np random dot rand int length of x data. The size is equal to batch size. And then I'm going to create my feed dictionary. So that's going to be x placeholder. I'm going to send that x data rand ind. We'll say y placeholder, and we'll set that to y true at that random index. And then finally I'm going to say session run train, where I define the feed dictionary as feed. Okay, before we actually execute this cell and get the results back, I want to go line by line what's actually happening here. First thing we need to realize is I'm going to feed in 1,000 batches of data where each batch is 8 corresponding data points, where we have an X data point and the Y label. Remember, this is supervised learning. To make sure that these batches are useful, I don't want to just send 8 by 8 by 8. Instead, what I want to do is grab 8 random data points from my data set. the way I can assure that is by creating this variable right here. And the reason it's called rand_ind is because this is going to correspond to a random index. So I'm going to use np.random.randInteger. Remember, that just returns a random integer. And I'm going to grab a random integer from 0 up to the length of x data. And kind of as shorthand, you can just pass in length of x data. And then I want to make sure I grab 8 of those. And those are going to be my index points. Then I'm going to use those random index points, pass them into my x data and the corresponding y true, and now I have my feed dictionary. Then I run that into this training optimizer, and there you have it. So that's the reason of these two lines right here. This random index actually chooses the 8 index points that are going to be part of that random batch. So you want to make sure that these batches are basically just a batch size number of random points from your data. So we're essentially going to train this model on 8,000 data points, and hopefully that should be enough for a good fit. So once that is done, I'm going to grab the actual predicted model M and model B. So that's the slope and the intercept. And we're going to say session.run and go ahead and grab those placeholders, so M and B. Okay, let's run this. Should be relatively fast depending on your computer. I'm running this on a pretty fast computer, so this may take a little bit of time for you. If it's taking too long, just reduce the number of batches. Let's go ahead and check out our model M. But before I run this, I want to show you what we initially started off. Remember, model M was a variable that started off as a random 0.81. The true slope should be pretty close to 0.5. So if we come back up here, the true slope I said was 0.5. So let's see how we did down here. If I run model M, so there it goes, 0.52. And remember, we added noise in there, so that pretty much makes sense. And again, the bias that we initiated with should be 5. The variable started with 0.17. Let's see how it did. We'll say model B, and there we go, very close to 5 as well. So essentially, we're doing extremely well given that we added noise to the data set. We can actually visualize these results quite easily. I can just say y hat is equal to my x data times my model B, or excuse me, model M, plus my model B. And then I'm going to say my data sample 250 points again, plot this out as a scatter plot where x is my x data column and y is my y column. And then I'm also going to say plt.plot x data versus y hat. And then let's make that a red line. So I run this and I can see I have a pretty nice linear fit there. And what I can also do is then kind of play around with the batch sizes. Let's see what happens if we run this for 10,000, how much difference it makes. Remember, we did add noise to this data, so it may not make a whole lot of a difference. You can see here now it's pretty much 5 exactly, and we're getting a little closer to 0.5 there. Not going to be a huge difference in this actual plot. Maybe you notice it a tiny bit that it dropped, but essentially we're getting a good linear model fit. And remember, we have noise to our data, so we can't expect it to be absolutely perfect. All right, so definitely go line by line on this. Make sure you understand each step. The main ideas are to, once you have your data, create the variables, create the placeholders, define the operations in your graph, define some sort of error or loss function, set up the optimizer, set up the trainer, initialize those global variables, and then if you have a huge data set, you also want to somehow feed the data in batches that are basically random batches from your large data set. And a lot of times, that's the hard part, actually figuring out how to grab those batches of data. As you'll see later on in future lectures, it's kind of challenging sometimes to work on a new data set and feed it in batches. All right, that's it for this kind of part 1. In part 2, we're going to jump right back into the notebook where we left off here and show you how you could do this whole thing with the tf.estimator API, which is going to make your life a lot easier. And we're also going to show you how to perform a train test split. Technically, we've been doing this kind of wrong. We haven't been doing the train test split. So let's go ahead and do that as well once we have the estimator API in place. I'll see you at the next video.